Overfitting is often avoided in many machine learning applications by using either regularization or ensemble methods. Dropout is an interesting ensemble method which is specifically designed for neural networks, and it can also be viewed as a regularization technique. This is because dropout can be viewed as the addition of masking noise added to the inputs as well as the hidden layers. In this video, we will briefly discuss the overview of dropout and the reasons why it works effectively. The process of training a neural network often leads to a high level of dependence among the features. This dependence extends not only to the features but also to the weights in the neural network. Part of the reason for this is that the different parts of the network they train at different rates. And this causes some parts of the network to adapt to others. This type of adaptation, which is caused by training inefficiencies in the neural network, is referred to as feature co-adaptation. Now, while we always want the features in the neural network to work together to make predictions, not all the dependencies that are learned are informative. Dependencies which are caused by inefficiencies in the training process are uninformative and they are sensitive to the nuances of the specific training data set. These types of dependencies, they often result in overfitting. Dropout is a method to reduce this effect. Now, in order to understand feature co-adaptation better, we will provide a simple example of one-way adaptation. Of course, co-adaptation is a lot more complex than the simple example that we will provide, but this example still provides the basic intuition of how feature co-adaptation occurs. Now consider a single hidden layer neural network and all edges into and out of half the hidden nodes. So you have a single hidden layer and all edges into and out of half of the hidden nodes are fixed to random values. You never update them during backpropagation. Only the other half are updated during backpropagation. So imagine you train a neural network this way with some kind of training data. It could be, for example, a linear regression problem or a nonlinear regression problem, depending on how you choose your hidden layers. Now, what will happen in this case, interestingly, even in this case, at least on the training data, you can often get reasonable predictions. Because what happens is that even though you are updating half of the weights, half of the features and half of the weights in the neural network, they will adapt to the other half. So even though half of the features are random features, the other features will work together with these random features to make reasonable predictions. Of course, these types of predictions, they are not optimal from the point of view of predicting on out of sample test data. Now, feature co-adaptation is natural in neural network where the rate of training varies across different parts of the network over time. Here we showed a very extreme case where there is no training on one part of the network and there is training only on the other part of the network. But in general, even when you're training a neural network, the different parts of the network do not train at the same rates. And as a result, co-adaptation of features as a result of these training inefficiencies is natural. And this type of co-adaptation, why is it bad? The reason it is bad is that we want the features working together only when they are essential for prediction. So very often it may be the case that using certain features together, you may be able to predict a class variable better than if you use the individual feature. So, but in most cases, what you want is these small groups of essential features. But what we don't want is features adjusting to each other because of inefficiencies in training. Because these types of dependencies are specific to the training data you used for learning. And it does not generalize very well to new test data. So what we really want is that we want our neural network to have many groups of minimally essential features for robust prediction. So imagine you had a single hidden layer. What you want is many groups of minimally essential hidden features. This will lead to better redundancies. What we don't want is a few large and inefficiently created groups of co-adapted features because this will typically lead to overfitting. Now, let's look at the basic dropout training procedure. How do we avoid these types of redundancies? So what we do is that for each training instance, we sample each node in each layer except for the output layer with probability P. So you will sample the nodes in the input layers as well as the nodes in the hidden layers. What we'll do is that of course, if you drop a node, you'll have to drop all its edges. So you can keep only edges for which both of its ends are included in the network. Now, what you do is that you will have a downsampled network, and you perform forward propagation and back propagation only on sampled network. Now here we are discussing for a single training instance. There are variants of this which work for a mini batch of training instances. Now note that the weights are shared. You have different sample networks for each training instance, but the weights are shared between different sampled networks. Now, with this kind of sampling procedure, you can also have an equivalent testing procedure. So what you do is that you perform repeated sampling like training. So again, you are performing the dropping out of nodes in a similar way. And then you average the results. Now, of course, if you're predicting probabilities, as is common in many neural networks, what you want to do is geometric averaging. So when you have, so for example, if you're predicting different classes, you will be performing geometric averaging of the probabilistic outputs for the different classes, and then of course you'll be normalizing the outputs to get the probabilities. Now, but of course, this type of procedure is inefficient. It's useful for developing bounds on your results, but in general, this is not the approach that is used. The more common approach is what is called the weight scaling inference rule. So what you do is that you keep the whole neural network, but you multiply the weight of each outgoing edge of a sample node I with sampling probability Pi. And then you perform a single inference on the full network with the downscaled weights. So why does this approach work? The reason this approach works is that when you have multiplied the weight of each outgoing edge of a sampled node with sampling probability Pi, the expected input into a node is the same as one that you would get from sampling because of the way you have downsampled it. So it's still getting the same expected inputs that you would get. Now, this weight scaling rule is not exact, particularly if you have nonlinear hidden units, it's not exact, but from a heuristic point of view, it actually works quite well. So, why does dropout help? The reason that dropout helps is that by dropping nodes, we are forcing the network to learn without the presence of some inputs. So it resists hidden units, for example, adapting to each other. Because what happens is that sometimes the hidden unit will have to predict the training instance without many of its sister nodes present in the network. So in this case, it will naturally resist co-adaptation unless the features are truly synergistic, in which case it will learn over many training inputs which ones really depend on one another. And what this will tend to do is that this will tend to create many smaller groups of self-sufficient predictors rather than creating a small number of larger groups of predictors. And many groups of self-sufficient predictors will have a natural model averaging effect, which shows why it's an ensemble-like technique. Now, this is the ensemble perspective. There's also a regularization perspective on neural networks, because when you drop a node, essentially the output of that node is zero. So you can view this as a kind of masking noise. So as we'll see later, in certain types of neural networks like denoising autoencoders, you apply masking noise to some of the inputs. Here you apply the masking noise both to the input and the hidden layers. And we already discussed in an earlier lecture that adding noise is equivalent to penalty-based regularization. That is, in the lecture on penalty-based regularization, we actually discussed this result. And you know, the way in which this regularization is done, it forces the weights to become more spread out. The updates are distributed across the weights because of sampling. It makes the weights more even, which is basically what penalty-based regularization also does. Now, there's some practical aspects of dropout in terms of how it's used. The typical dropout rate, that is probability of exclusion, is somewhere between 20% and 50%. The exact value you can probably learn by hyperparameter tuning. And it's better to use a larger network with dropout to enable learning of more independent representations. And dropout is applied to both the input layers and the hidden layers. In some cases, the dropout rate in input layer is a little bit different than that used in hidden layers. That is another tuning that one can do. And typically, one tends to use a large learning rate with decay and large momentum. And one issue with this, of course, is that what could happen is that if you use a large learning rate, you could end up with weights that tend to become large very quickly. So one thing that you do is that you impose a max norm constraint on the size of network weights. So what you do is that the norm of the input weights to a node is upper bounded by a constant C. By doing this, the learning is more stable and the generalization performance of the network is better.